speaker, Denis Bondar, to introduce.
Good morning from New Orleans. It's a great pleasure to be at this international seminar. By now, I know people, participants from many countries are coming, listening and participating. But today is a special day because it's a great pleasure to introduce my old friend, Professor Ramana. He has been for many years working at Princeton University, and currently he is a visiting researcher there on his sabbatical. But his permanent appointment is at the University of British Columbia. He is the Simon Chair in Disarmament and Global and Human Security. And so Ramana actually he's received many awards. So, for example, Guggenheim Fellowship in 2003. And then he published a book which is titled The Power of Promise, Examining Nuclear Energy in India in 2012. And in that book, he writes, in introduction to this book, I have to say I read like 40% of that book. So in the introduction to this book, he writes about the situation when his daughters approach him and says, "Oh, Daddy, what are you writing?" And he says, "Yeah, I'm writing a book." And they say, "Oh, is this going to be like Harry Potter?" And he says, "No, it's not going to be as interesting as Harry Potter." But nevertheless, the book is I found it very interesting as a kind of Ukrainian reading it about the India, new and independent country, how it comes to be and how it's, development of science and technology and nuclear energy from the very beginning, actually, even though it was quite a poor country at the get-go. So 2 years later, Ramana received in 2014 very prestigious award by American Physical Society named after Leo's Lizard Award. And if you look at the recipients of this award, former recipients include Hans Bethe and Andrei Sakharov in past. So, and this award was given with the following citation: for outstanding contributions to promote global security issue through critical analysis of nuclear weapons and nuclear energy programs. So also, Ramana is on the is a member of international panel on fissile materials and Canadian Pugwash group, and he's on the team that produces the annual World Nuclear Industry Report status. So, he's one of the most authoritative person on nuclear energy and everything nuclear to speak about. I personally look forward to his upcoming book to be published this summer, called "Nuclear is Not the Solution: The Folly of Atomic Power in the Age of Climate Change." Yeah, I guess the previous title was a little bit more mysterious, but now the title gives away the message of the book, I guess. Now, I would like to actually personally add that Ramana, back in 2022, wrote an article for Bulletin of Atomic Scientists, a very prominent newsletter, like a magazine for security and nuclear issues. It's famous for producing this doomsday clock and talking about the Nergodar. And I served as a translator from Ukrainian to English. And it was the very first article that mentioned, with that article, it was based on the interview done conducted with the head of the Atom Prof Spilka. This is a trade union of nuclear engineers of Ukraine, describing the situation back then, in the Nergodar, but from the point of view of nuclear engineers that run the plant. And it was the very first publication that drew attention to people, to actually, engineers, how it actually to work there. Since then, actually, many reportings kind of interview, but it was the very first one, to the best of my knowledge. So thank you very much, Ramana, for doing that, for standing by peace, by standing for Ukraine, right? And I also wanted to use this opportunity and to mention the Physicist Coalition Against the Threat of Nuclear Weapons. This is the link posted to this coalition in the chat, and I'm personally a member of this coalition, and so is Professor Ramana. And this coalition is it's an international network of physicists. You can get engaged with this coalition. You can become a member. It's free, and it's open to every physicist, even undergraduates, right? Any physicist at any level of profession. And the aim is to basically to in a way to talk about nuclear weapons, their danger, and to conduct international science diplomacy against these very, very, very terrible weapons. So with all, so thank you very much, Ramana, and microphone is yours.
Thank you, Dennis. That was a very, I'm honored to be here, and I'm a little humbled by your introduction. I'll try my best to sort of live up to that. Let me start by sharing my screen and saying, once again, it's my great honor to be here. Thank you so much. So my task here is to talk a little bit about nuclear accidents and in particular some of the physics elements in it. But before I go on to that, I will sort of start by saying some more general things about nuclear energy. One that I don't need to explain to you, given that you're hearing often about the Zaporizhzhia nuclear plant that Dennis was mentioning, and more historically, the Chernobyl accident from 1986 and its long-lasting effects, that nuclear power is unique among all energy generation technologies, electricity generation technologies, in that it is capable of massive damage to environment and public health, which the damage, which is primarily from radioactive contamination, is spread out in space and time, in that if there is a severe accident, as happened in Chernobyl, as happened in Fukushima, the radioactive contamination can spread out a lot in a very large area of space. And the effect is long-lasting because some of the radioactive materials, in particular cesium-137, which is the primary long-term contaminant, because it has a half-life of 30 years, it is going to be radioactive for a period of up to roughly 300 years. And the only thing that is going to mitigate that, the radioactive releases from that, would be the changes because of weather and the material sinking under the soil. But still, there are large parts of the world which will be contaminated for very long periods of time. Now, why is this even a concern? Why should nuclear power plants be susceptible to accidents? At one level, it's because nuclear reactors are a very complex technology. It has multiple parts, many different processes that are happening simultaneously, which also means that there are a large number of possibilities for things to go wrong, for failures to happen, for events to progress in ways that you don't expect. Plus, nuclear power plants have large quantities of radioactive materials, and these are often at high temperatures and/or pressures. The result is that in the event of an accident, large energy releases are possible. And this energy release means that the radioactive material can be lofted fairly high into the atmosphere, and following which it can be spread over these large areas by the wind. The last thing which I want to say is that the time scale for many of these processes is set by nuclear fission and how fast it can progress, as well as a number of other physical processes, all of which mean that the events that can occur at a nuclear plant can occur at a very rapid pace. So once things go wrong, it can happen very, very quickly, and leaves the operators of the nuclear plant very little time to be able to intervene and maybe control the process. So these properties have been combined, have been looked at by many people, where in particular, there was a sociologist called Charles Perrow who started looking at nuclear reactors in the context of the accident that happened in 1979 at the 3 Mile Island nuclear plant in Pennsylvania in the United States. And Perrow sort of analyzed what went wrong there. And then he didn't stop with just that accident, but he went on to analyze a number of other technologies which have similar hazardous potential, which seem to be having accidents. And he identified 2 kinds of properties that he thought were unique or that caused these accidents. Those properties he called interactive complexity and tight coupling. So interactive complexity is something which is fairly intuitive. So you have a complex technology, which means that there are multiple parts of it. And in certain cases, these multiple parts will interact with each other. So the failure of one part might lead to a failure of a second part. Or a different safety safety component, for example. And so there are a number of different pathways to an accident. And the other feature that Perrow identified was called tight coupling. So tight coupling is when events are occurring at fairly rapid progression, one quickly leading to the other, leaving very little time for intervention in case something goes wrong. So an example that I like to give is if imagine, Dennis were to fly to Kiev, or one of you were to fly to the United States, it's quite possible you might have to change flights, let's say at London's Heathrow Airport. And if the time between when your first flight is landing and when the second flight is about to take off is a very short period, let's say just half an hour, then by the time you get off the first plane, you will have very short period of time to be able to walk to the second terminal, to the second gate to board the next flight. Now, in that very short period, let's say you have just 10 minutes, any minor mistake can lead to a problem. For example, you forget to lace your shoes and suddenly you stop to lace your shoes, or you've forgotten to zip your bag and as you're walking, everything falls out. So you have to stop to pick up everything, including your passport and everything. And those few minutes might lead you to miss the second flight. That's what one might call a tightly coupled situation. In contrast, if the flights are separated by, let's say, 6 hours, then these small failures will not matter, right? So this was a second characteristic that Perrow identified, and he noticed that in many technologies, these are essential components. Now, you might think, we can always loosen the coupling, which is to say, for example, going back to the example that I mentioned of 2 flights, you could always choose tickets that are separated by many hours. But the challenge there is twofold. One is time is valuable, so you might not want to spend 6 hours sitting in Heathrow Airport. It's not the most fun place to be sitting in. And so you might prefer a flight between that have a fairly short period between them. And secondly, there could be challenges which have to do with costs. Now, when you're designing technologies, whether it's a nuclear reactor or a petrochemical plant or something, you always have to balance multiple priorities. And that means sometimes you will make decisions about the design that lead to tight coupling. And anyway, Perrow's insight was that these 2 characteristics, interactive complexity and tight coupling, will inevitably lead to serious accidents. Inevitably does not mean that it's going to happen all the time. It could be fairly rare, but you cannot say that the probability is zero, that it is never going to happen. So in these kinds of technologies, you always have to be prepared for accidents, severe accidents, and this is what he called normal accidents. And since Perrow's book, which came out first in 1984, sociologists and organizational theorists have applied these theories to a number of different technologies, finding that, this is a fairly robust insight. The other insight into dealing with these hazardous technologies like nuclear plants came from another group of social scientists who mostly at that time were at the University of California in Berkeley. And they were called the High Reliability Organization Group because they were looking at some organizations that deal with similar hazardous technologies, but they found that some of these organizations seem to be doing better than one might expect, that they have fewer accidents or no accidents. And so the HRO group tried to understand what it was that these organizations were doing that was different, that allowed them to operate these reactors and other technologies safely. And they came up with a number of stringent demands. I'm not going to go into all of those things, but had to do with certain kinds of flexibility and so on and so forth. And they basically concluded that these demands are very stringent, that it's unlikely that most organizations that manage hazardous technologies will actually meet all these demands. And in the book that Dennis mentioned about nuclear energy in India, I tried to see, me and a colleague of mine called Ashwin, we tried to understand whether these demands posed by the HRO group were applicable, or the Indian Department of Atomic Energy and the Nuclear Power Corporation of India, which manage all the nuclear reactors, whether they actually meet all these stringent demands. And our answer was in the negative, that we found that those organizations did not actually operate these plants as safely as possible. Now, the fact that they have not they don't operate safely does not inevitably mean that accidents are going to happen. It just means that the risk of accidents is higher than if they were a well-functioning organization. That's because accidents, by their very nature, are a matter of luck. It's not that, and luck is not something which is going to say, oh, you're a good organization, I'm going to benefit you, and some other organization is a bad organization, so therefore I'm going to come and cause an accident there. So it's a matter of luck and a matter of time before such places have accidents. So the one result of the way of thinking that Charles Perrow and others envisioned was that, or promulgated, was that the usual methods that are used to estimate the risk of serious accidents, the so-called probabilistic risk assessment methods, they calculate what the frequency of a serious accident is. They are often misleading simply because they cannot possibly envision all the different ways in which an accident can happen. So, for example, in the case of the Fukushima accident, they had not envisioned the possibility of not just a tsunami of the size that hit the plant, but also the fact that their diesel generators would be flooded and therefore not capable of working. And so that was something which none of the planners for none of the designers of the Fukushima reactor and the Fukushima nuclear power plant had taken into account. The other insight is that the usual way we try to deal with risks of accidents and in general safety is to add redundant safety features. But this can actually make things worse in certain circumstances because of the reason that Pero mentioned, which is one component can interact with the other. In the case of redundancy, the problem is that sometimes one of the safety features fails, and that failure in turn triggers the failure of other reactors. And I'll talk about one example of this later on. The other challenge with this is how any kind of regulator can examine and assess the safety of hazardous technologies, including nuclear reactors. The problem is that because reactors are very different from other kinds of technological artifacts, you have to have absurdly low failure rates. I mean, if you look at numbers that any nuclear reactor designer would offer as the risk of an accident, as the frequency of a potential accident, severe accident, those would be extremely low. 1 in a million years, 1 in 10 million years, 100 million years, those kind of numbers. And for these kinds of numbers, one cannot statistically verify this because we don't have the kind of actuarial data, the data from multiple facilities and many years of operations to be able to verify that safety. In this sense, nuclear reactors are very different from, say, airplanes, where we know that accidents happen, but we still want a fairly low failure rate. And you can see whether that failure rate is being met or not by looking at the thousands and thousands of airplanes that are flying in the skies on any given day. All of that is providing data for how often certain parts of the planes fail. And in the case of nuclear power plants, on the other hand, that kind of empirical data is not available, which means that regulators have to make subjective judgments. There are uncertainties, and there are also organizational conflicts, all of which mean that it's very difficult to prove that or confidently assert that a nuclear plant cannot have an accident. There's also phenomena of overconfidence by nuclear authorities, who often feel that they know all about a nuclear plant and can be sure about how the accidents can or cannot happen. And there's also failures of the regulator because of the challenges that I mentioned earlier. As well as finally, nuclear power is a very political technology. There are lots of different agencies around countries that have some kind of input into setting up nuclear power plants or not. I don't want to comment about what's happening in Ukraine, but I'll just very briefly mention that I see these announcements about Ukraine wanting to set up new nuclear plants, and clearly that's not a safety-related decision, is what I would say. But the example that I've studied much more about is the case of China, where you could see these obvious conflicts of interest between the Chinese central government, which wanted a rapid scale-up of nuclear power in the country because they want to become an exporter of nuclear reactors and be seen as a modern power with certain kinds of technological capacities and so on and so forth. And then the other set of players which are important in China were provincial governments, which wanted nuclear projects in their province because they would get federal funding from the central government for projects that happen in their province, which means that their province will get economic advantages. And so they are not as concerned about the safety. For example, they have called for building nuclear plants in what one might call inland sites, sites where the cooling water comes from rivers or from lakes, which raise the possibility that in the event of an accident, that the river or the lake would get contaminated by radioactive materials, which then would lead to impacts all along the banks of the lake or along downstream in the river. And lastly, there are also a number of state-owned enterprises. The equivalents would in the United States would be private corporations who would want to achieve market share. In the case of China, that meant that they were promoting new and untested nuclear reactor designs, all of which made China into one of those cases where safety was actually suffering because of all these other priorities. Finally, I'll also say, because this is a physics audience or a scientific audience, one claim that you see quite often made by nuclear reactor vendors in recent years is that their designs are based on passive safety. And therefore, passive safety means that the safety mechanisms have to do primarily with the laws of physics as opposed to some kind of external technology. For example, a pump that would pump in water in the event of an accident, so that the water is the one that's going to take away all the heat. The basis for so the claim is that because these safety mechanisms are based on the laws of physics, we don't have to worry about whether there is power in the building, whether the diesel generators work or not. And this is actually an old idea, because in nuclear reactors, there are safety features that are essentially passive, that don't require any kind of human intervention. For example, the building that most people would associate with a nuclear power plant, the containment building, is a straightforwardly passive structure. It's just a large structure made of concrete and steel, and it's capable of withstanding a fairly high pressure of gases inside without letting any of that going outside. And that's its safety function. But the problem with these is that at some point, these systems can fail, either because their design capacity is exceeded. So for example, in the case of containments, I'll talk about the fast breeder reactor in India, where the expected energy releases in the event of a certain kind of accident are so high that the containment will fail. The second challenge with passive safety is that you cannot, as the operator, control how fast it operates. So to give an the challenge with most nuclear reactors in an accident scenario is to transport away the heat that is produced from the radioactive fission reactions that are happening inside a nuclear reactor, even after it was shut down. My colleague here in Princeton University, Rob Sokolov, termed this the fire that cannot be extinguished, or the fire that cannot be put out. Because these the radioactive decays continue happening regardless of what you're doing, you have to find ways of taking out the heat that they will produce. And this was the main challenge at Fukushima. The problem is that if you're going to rely on passive mechanisms, like for example, the example of a chimney, where the passive mechanism is basically that the hot air rises through the chimney, and along with that, all of the smoke goes through the chimney. And so you as a person who lives inside the room, you're not exposed to the smoke. So that's a passive safety mechanism, or a passive mechanism for reducing the pollution inside the room. The problem is that you cannot change the rate at which the smoke is being wicked away, that the hot air is going up. It depends entirely on what is the diameter of the size of the chimney, the conditions outside, and so on. Unlike in the case of a heat pump, of a pump, for example, you can control how much water is being sent into the system, and if necessary, you can add an extra pump. Those kinds of capacities for control are not available in the case of passive safety. The second problem is that passive safety will depend on the conditions. So I mentioned the example of the chimney. Now, in most cases, the chimney works perfectly fine. But if there is a block up in the higher up in the chimney, or if soot sort of deposits itself, or under certain circumstances when there is rain outside or the wood is very wet, you will see that this mechanism will not work. And a lot of the smoke will come inside the room. This is why there are people who have fireplaces in their houses will occasionally have to invest in the services of somebody who can repair this. And these kind of unenvisioned situations happen a lot. In the case of Fukushima, the station superintendent later on said, we encountered a situation that we had never imagined. If you are in such a situation where you have not imagined, how do you design for that? That's the essential question. Okay, so the bottom line of all of this discussion is that the probability of an accidental nuclear power plant will always be uncertain and certainly greater than zero. So there's no such thing as safe nuclear power. Okay, now I'll also just as a aside, because again, I'm talking to people who are in the neighborhood of Chernobyl, I'll just say that, there is a huge political debate over what has been the result of that. And one historian, Kate Brown, who has written a very masterful book on Chernobyl, talked about how many of the authorities, especially in places like the International Atomic Energy Agency, were using a range of tactics that would try to underestimate the death estimates and systematically undercount stuff. She talks about classifying data, limiting what questions are asked, stonewalling investigations, block funding for research, sponsor rival studies, talk about natural risks and somehow compare these things, and set up sort of ways of studying that will only detect something in the event that there are very large numbers of deaths, and so on and so forth. So that's something which also you should remember when you're thinking about public discussions about the accidents. Okay, now I'll sort of turn to a slightly more technical aspects and talk about one kind of set of reactors and their safety challenges. So, nuclear plants are special in some ways, but they are also familiar in other ways. A nuclear plant basically is a very complicated way to boil water using a very hazardous process. But ultimately, that's what it is. It is producing heat, and the heat converts water into steam, and the steam runs a turbine to produce electricity. So you will see the pictures for a fossil fuel plant and a nuclear plant are essentially similar. Of course, in reality, they're going to look different, but in terms of trying to conceptualize what they are not that different from fossil fuel plants. This is different from, let's say, a solar photovoltaic plant where there is no steam involved. It is a very different process that is creating the electricity. So in any nuclear reactor, there's going to be fuel. The fuel contains the fissile materials, which would be either uranium-235 or plutonium-239. Those two isotopes are the two known fissile isotopes. There's also uranium-233 for those reactors that might involve thorium. And then there are fertile materials, which are materials that can be converted into fissile materials upon absorption of a neutron. For example, uranium-238, which is the most dominant isotope of uranium in nature, that can be converted into plutonium-239 when it absorbs a neutron and undergoes a series of radioactive decays. All reactors will have to have some kind of a coolant to remove the heat from the core. They will have to have some kind of a control system to maintain the criticality of the nuclear reactor at all times. There might be a moderator that would be used depending on whether you have a nuclear reactor that is operating on the basis of thermal neutrons, slow neutrons, or fast neutrons. If it's a fast neutron reactor, then you don't need a moderator. In fact, you should not have a moderator. And then there could be a reflector to reflect back neutrons so that you don't have to have a very large reactor. So if too many of the neutrons escape the reactor, then you would have to have a much larger amount of fissile material inside the reactor to be able to continue with the chain reaction. There could be a blanket outside to absorb neutrons in the event of you're trying to design what are called breeder reactors. There would have to be shielding to absorb all the kinds of radiation that will be generated inside the reactor, especially the more penetrating gamma rays, and protect all the people who are operating the reactor, and emergency systems to prevent the reactor from malfunctioning. So as I mentioned, there are these kinds of materials which are fissile materials which are can undergo fission by absorbing neutrons of any energy, including low energy. The two main ones are uranium-235 and plutonium-239. Fissionable materials which can undergo fission, but they would require neutrons above a certain energy threshold. For example, uranium-238. And then materials that are what I call fertile, which could be transmuted into a fissile material upon absorbing a neutron. I talked about uranium-238 becoming plutonium-239. Similarly, thorium-232 can become uranium-233 by absorbing a neutron and undergoing some radioactive decays. There has to be a coolant that transfers heat. Some of the examples, the most dominant reactor design around the world uses light water, regular water, but except that it's purified. The reactors in Canada, where I work, are heavy water moderated and heavy water cooled reactors called CANDU designs. And then there are reactors that use gases like carbon dioxide and helium. Moderators, I mentioned, they slow down neutrons. The examples are light water in most reactors or heavy water, and in some cases there could be also graphite. And in so-called fast neutron reactors, you don't want to have a moderator because you want the reactor to be operating in the fast neutron spectrum. Okay, so I'll now talk a little bit about accidents in the case of fast reactors. And these have to do with feedback loops of certain kinds. And this is a different kind of an accident that is capable of happening primarily in fast neutron reactors. So in the so-called breeder reactor, because these are operating in the fast spectrum, you have to have a fairly high concentration of fissile material, either plutonium or enriched uranium, because the cross section for fission at high energies is much lower. That is the reason you have to have a high concentration of this fissile material. If you design your reactor appropriately, then in principle, you could have more fissile material produced in the so-called blankets, which absorb the neutrons that are going out of the reactor. So in the picture on the left, the black outermost circle is the shielding, and then you would have the coming inside. There are sort of the third area, the gray area, is what is called the blanket, and the blanket is the one which absorbs all the neutrons. And if that blanket is made of something like uranium-238 or thorium, then the U-238 will get converted into plutonium. And again, depending on how the reactor is designed, you could design it to produce more plutonium-239 than is being fissioned in the core of the reactor. And this is what was considered to be extremely attractive about these reactor designs, especially in the early years of the nuclear age, the 1950s, 60s, and 70s. And this is for two reasons. There was a concern then that the world had fairly limited amounts of uranium, especially cheap uranium. And the concern was also that nuclear power would expand very rapidly, because of which we will run out of uranium to be fueling them. And therefore, we have to go towards breeder reactors that can use the more plentiful uranium-238 isotope in nature. In regular light water reactors, U-238 barely contributes to any of the fission. Now, both of those assumptions about running out of uranium and nuclear power growing rapidly have since been proven to be wrong. We have much more uranium that people knew about in the 1950s and 60s. Nuclear power has proven to be a fairly minor contribution to the global electricity supply. Around the world, nuclear reactors supply only about 9% of the world's electricity at this point. The highest it ever was in the mid-90s, when it was about 17.5%. Since then, it has continuously declined, and the expectation is that it will decline further in the future. And this is for reasons which we can go into during the question and answer if you're interested. Okay, so coming back to fast breeder reactors, the reason why people were interested in trying to produce more fissile material than was consumed in the core was because of the concern that we would run out of uranium, and that is no longer true. But fast breeder reactors, fast neutron reactors in general, even whether they breed or not, have received a new breath of life, as it were, because of the advocacy of some prominent people. One of them is shown in this picture on the top, the person all the way to the left, Jim Hansen, who is probably the United States' most celebrated climate scientist. And for many, many years, Hansen has argued that nuclear power is the only viable way forward on climate change. I disagree with that, but that's a separate point for now. But what he sort of argues in particular is that the problem with nuclear power is the challenge of dealing with nuclear waste, radioactive waste. This problem can be circumvented by building what are called fast nuclear reactors. And he wrote a whole book, or a book in which this is a fairly prominent part, called Storms of My Grandchildren. I've sort of tried to explain why this is not true in an article that I wrote at the same time, soon after that. The other prominent individual who has been pushing for fast neutron reactors is Bill Gates, who has invested in a company called TerraPower. And TerraPower, he says, we are, it's an innovative design, it's a fast neutron reactor design, and it's going to be safer because it uses liquid sodium to cool the reactor instead of water. And because sodium can take away heat much more efficiently than water, you don't have to pressurize the sodium. And this, Bill Gates claims, is a safety advantage. There's a problem with that. The problem with that is sodium. Sodium, as all of you must know from your high school physics or chemistry, is a very difficult material. In particular, it doesn't react very well with either air or water. And because of these chemical properties of sodium, which are essential to sodium, doesn't matter whether it's a reactor designed by a software billionaire like Bill Gates or not, sodium is going to behave that way in all reactors. These chemical properties of sodium mean that there are lots of operational and safety issues, which have plagued a large number of reactors, fast reactors that have been built around the world. And we see that in almost all these reactors, there have been a number of sodium leaks. So the second table here shows the numbers of leaks as of 2008, so quite some time back, the history of sodium leaks. I have not seen a more recent study of these, so I don't have more up-to-date data about this. But that has also meant that most reactors, fast reactors, have operated with fairly low, what are called load factors, which is a measure of the efficiency of the reactor. As you will see in the first table here, there are only two reactors, fast reactors, that have had somewhat high load factors. The BN600 and BN800 both operated in Russia. In both cases, there are some questions about how safely the Russians are operating. There are stories about how there have been sodium fires, but the operators continue to operate the reactor regardless of the safety challenges with operating a reactor under such circumstances. What they seem to have done is to prioritize operating the reactor continuously over operating it safely. And again, there's probably a chemical reason for why there are all these leaks, which have to do with sodium, but also sodium interacting with the carbon that is contained in the metallic components of these reactors. These interactions are probably what caused the corrosion in the system's metal parts, eventually leading to leaks. I mean, the experience we've had with other fast reactors has been pretty poor. I think the most telling example is from France. Long the poster child of nuclear power around the world, which built the Super Phoenix on the basis of experience with something called the Rhapsody reactor, and also the Phoenix reactor. First was a test reactor, and the second was a pilot scale plant. But the Super Phoenix operated really poorly. It was shut down because of a series of accidents and other problems. And the end result was that the Super Phoenix operated with about 7.9% cumulative load factor, which is that it operated for less than 8% of the time at full power than it should have. And so that's a really telling example. There's also a particular concern, safety concern about fast neutron reactors, which have to do with feedback loops. In light water reactors, the most dominant type of reactors around the world, the fuel is often in a configuration where if the fuel is displaced from the optimal configuration, then the reactivity will go down. And this is a kind of negative feedback loop, if you like. In fast neutron reactors, on the other hand, the fuel is not in the most optimal situation in terms of the reactivity. And if the fuel changes position, for example, due to melting, then that can increase the reactivity, which then means there will be more heat production, which then means there will be more melting of the fuel. And that can be a positive feedback loop. And this can happen also because when there is increased heat in one particular local region, the sodium will start vaporizing. You can have bubbles of sodium inside the molten sodium. That reduces the density of sodium inside those bubbles, which then lowers the amount of moderation that the sodium will do, slowing down of neutrons, which then will also increase the reactivity. So this is another feedback loop, which both of these sort of mean that fast neutron reactors are susceptible to a certain kind of accidents called core disassembly accidents. Now, in under normal circumstances, you have the fuel and the molten sodium enters it from the bottom of the structure. It rises because it is absorbing heat and it's becoming more buoyant, and eventually it comes out through the top, and it goes out and it transfers its heat through some kind of heat exchanger to water, which then becomes steam, and so on and so forth. Now, in one example, in the case of the Fermi reactor in Michigan in 1965, there was a safety system that had been added called a core catcher. And the core catcher's job is to try and prevent recriticality in the event of a reactor meltdown. Now, in the core catcher contained mostly of pieces of zirconium that would basically, that was supposed to serve the safety function. Now, 2 pieces of zirconium got loose when the sodium was flowing, and they went and got stuck in some of these channels, thereby blocking the flow of sodium in a couple of these channels. When the sodium transfer was stopped, the fuel started heating up and started melting down, and then that reactor had to be shut down immediately. But in the event that the reactor is not shut down for one reason or the other, then this feedback loop will mean that the reaction will progress. More and more of the sodium fuel will start, the fuel will start melting, and the fuel will become a molten pile, which means that the reactivity is so high that the fuel will start actually vaporizing at some point, leading to the possibility of an explosion, which can essentially produce so much energy. In the case of a fast breeder reactor that's being built in India, my colleague Ashwin and I calculated what the amount of energy that would be produced. And we found that essentially the amount of energy that could be produced is so high that it would essentially overwhelm the containment building for the prototype fast breeder reactor. And we also showed that the design of the containment was completely inadequate to the kind of energy that could be released in the case of the fast breeder reactor. Anyway, so that's, I think, the certain kind of a reactor accident that is peculiar to fast neutron reactors, and is a problem. I'll also just briefly mention that one of the motivations that Jim Hansen talked about, which has to do with nuclear waste. And he claims that fast neutron reactors can solve waste problems. Now, what is this problem of nuclear waste? And I'll sort of say a little bit about it. The main problem is that in a nuclear reactor, you're going to be producing radioactive materials that stay radioactive for millennia. There are some fission products, for example, some of the cesium isotopes and some of the iodine isotopes that have half-lives in the hundreds of thousands of years or millions of years. And so for that very long period of time, this waste will have to be segregated from human contact, because any contact with it will create radiation doses to the people who are exposed to it. Now, in a fast neutron reactor, what you can do is to operate the reactor using one very narrow class of these radioactive materials produced in reactors, the so-called transuranics, in particular plutonium and uranium, the higher isotopes of uranium and so on. Those are the only ones that can be used in a fast neutron reactor. The rest of the materials, all the fission products, cannot fission, and therefore they cannot be used as fuel in a nuclear reactor. And so that problem will persist even in the case of a fast neutron reactor. The only difference is that in order to make the fuel for these fast reactors, you have to do this chemical process called reprocessing, which will separate out the fission products from all of these transuranics. When you do so, the fission products move from being inside a very stable, solid environment to a liquid state, which is much harder to control. You might have to vitrify it and stuff like that, which raises other risks. But the bottom line, again, is that the radioactive materials don't go away. And so for the problem of nuclear waste remains, even in the case of fast reactors. And these are technical challenges which have to do with the specific, the long-lived radioactive nature of this, coupled with a lot of social concerns about people who don't want their descendants to be exposed to this risk of a repository of nuclear waste leaking from a repository, means that there are no operating nuclear waste repositories anywhere around the world. There is no demonstrated solution to nuclear waste. And I'll also just briefly mention that social scientists who have studied how the public reacts to nuclear power have noted that nuclear power has a special distinction in the literature on risk perception. It is to date the technological hazard with the most negative and most problematic constellation of traits, which makes it very hard to manage socially and politically. This is a quote from a paper by Paul Slovic. Okay. I'll also very briefly mention the point that Dennis raised in this introduction, which had to do with the Physicist Coalition Against Nuclear Weapons. Nuclear energy is closely linked to nuclear weapons because it involves the use of and production of either enriched uranium or plutonium. Both of these materials can be used for fueling reactors, but they can also be used to make nuclear weapons. When you have a country like Iran, for example, or any other country that has enrichment capacity, the capacity to enrich uranium, that whether they enrich it up to typically 3 to 5%, which is the levels at which most nuclear reactors are fueled, or maybe 15 to 20%, which is the case for many of the fast neutron reactors, or if they enrich it up to 80, 90%, which is the typical enrichment required for nuclear weapons, that is a decision they are going to make. Likewise, all nuclear reactors will produce plutonium in their spent fuel. If a country chooses, it can separate out the plutonium through this chemical process, which I mentioned, called reprocessing, and use the plutonium to make nuclear weapons. What's also important to remember is that even a nuclear plant that is small in terms of how much electricity it produces relative to the typical sizes of power plants around the world, and more importantly, power requirements in multiple countries, even a small reactor will require enough enrichment capacity of uranium that can produce a sizable number of nuclear weapons every year, and also produce enough plutonium to produce a sizable number of nuclear weapons. So if any country has nuclear plants, then there is the possibility. It's a technical capacity, it's not a political decision. It's only when the country decides, and of course there are all these possibilities of what the International Atomic Energy Agency does and what the international community does, but it's actually quite hard for the international community to stop a country from going and building nuclear weapons if they have the technical capacity and they make a political decision to do that. This is one of the stories I think we can take from the case of North Korea. All right, so I'll just end with asking this question that some of you might have, which is whether there's a lot of talk about trying to use nuclear energy as a solution to climate change. And my answer, no surprises, is going to be no. But I'll say this is not a good idea because I don't think nuclear energy is a very desirable way to generate electricity. I already talked about the risk of accidents, the linkage with nuclear weapons, and the challenge of nuclear waste. But I think a lot of my research also shows that I've done a lot of work thinking about the economics of nuclear power and comparing it with other alternatives. And one thing we find is that nuclear power is among the most expensive ways to generate electricity. If you're going to have to build a new nuclear reactor, the estimated cost of these would be much higher. So in the United States, for example, the cost of a new nuclear plant and the electricity from that is estimated at something like 4 to 5 times that of the cost of building a solar plant or a wind set of wind turbines. And so it's not a very economical way of trying to deal with it. But there's an even greater challenge. A nuclear plant takes a long time to build. A typical plant takes about 10 years to go from the beginning of construction, which is usually set as the point at which the first concrete is poured in the ground, in the hole that is built to inside which the reactor is being built, to the point where it generates electricity and feeds it to the grid. That time period is of the order of about 10 years, typically. And then there is another period of 10 years before you start the construction, which is required to get the environmental consents, then meet the environmental assessments and requirements, find a community that is willing to live with this hazardous technology in its neighborhood, and last but not least, raise the tens of billions of dollars required to build one of these nuclear plants. All of that means that if for example, New Zealand or some, Venezuela or some country that doesn't have nuclear plants today, or Indonesia, were to decide today that they want to build a nuclear plant and use it to generate electricity, it will take them 15 to 20 years before the first unit of electricity actually flows. And that time scale is not compatible with the kind of time scale that climate scientists, including the Intergovernmental Panel on Climate Change, tell us is required to reduce our emissions. Okay, I'll stop there, and I'm happy to answer any questions if anybody has any. Thank you very much. Andre, you're muted.
We do not hear you, Andre. Even though you are unmuted, your microphone doesn't work.
All right. Thank you very much for a wonderful talk with many questions. And we have already two raised hands. Please, Maxim.
Yes,
Please
thank you.
start.
Thank you, Professor Ramana, for a very interesting presentation and information. I'm actually teaching nuclear physics of nuclear reactors to my students, and on the first lecture, I'd like to present some comparison between different sources of energy, and so I tried to find those estimates of the cost of nuclear energy and fatality, let's say. And usually, so I found information about the costs, actually levelized estimated costs of energy generation, and actually I found it on the site of International Energy Agency, and they at the top of most cheapest energy sources, there are nuclear, solar, and wind power. So and I think this levelized cost includes power plant construction and just sustaining, so energy production and construction. That's so. Is nuclear energy so expensive if the data presents even International Energy Agency that is more like, I would say, favorable in the for the sustainable energies like solar and wind, says that nuclear energy is on the level of solar and wind power. So
yeah, I think you have to dig deeper into the data and ask what they're actually comparing. Okay, and the IEA does not. I mean, I have not seen the specific data that you're talking about, but I will say two things. One is the IEA and similarly the Nuclear Energy Agency, which it is sort of associated with, and so on. These all have to rely on data that governments give. And there is a lot of, we don't have a lot of confidence in data, for example, that's coming out of China, right? Or various other countries as well. So that's one challenge. The second challenge is they are not often comparing the cost of construction of new nuclear plants based on empirical numbers of how much it is being costing right now. So in the United States and in Western Europe and so on, we have a greater transparency. And so I would suggest that you look at some of the data that is available in these countries. So for example, in the United States, there is a company called Lazard, a Wall Street company, which does this annual comparison. And in the chat, I put a link to this World Nuclear Industry Status Report that Dennis mentioned in the introduction. This is an annual report that I've been part of, and in which we, in these reports, we try to report what we find about data from around the world. And the Lazard numbers from different years are usually summarized in this data. So I suggest that you look at that. And also lastly say, so, you can think about this in multiple ways, and, calculating the levelized cost involves a large number of assumptions about, the cost of construction and so on. If you look at the specific assumptions about it, and you can do the calculation yourself and say, let me take the cost of construction of any of the newly of the constructed plants. So for example, the Vogel plant in the United States, or the Olkiluoto plant in Finland, or so on and so forth. You take those numbers, actual numbers, calculate what is the per kilowatt cost, run through the levelized calculation, and I will assure you, you'll find numbers which are much higher than solar and wind, right? And that's for a simple reason. Nuclear plants today are costing something like $15,000 to $20,000 per kilowatt of construction. And a solar plant or a wind plant are of the order of $1,000 to $2,000 per kilowatt, probably even cheaper in some cases. Right? That's a huge difference. And regardless of the fact that a solar plant has a much lower capacity factor and so on and so forth, there is no way a nuclear plant can be cheaper or even comparable to those plants. Right? So I'll just invite you to just try to do this calculation yourself used on real data.
Okay, thank you. And may I have another question?
Yes, please.
Thank you. Yeah, so on the death ratio, I also tried to look into the data, and apparently the most fatal were actually coal and gas and oil. And then again, nuclear was, if we calculate a number of deaths per number of per amount of produced energy, then because of nuclear power plants are produce a lot of energy, they have this ratio per number of, per amount of produced power is at the levels of wind and solar. I mean,
yeah. So that's again, that's a political question, right? You have to look into dig deeper into the data to understand what they are comparing, right? And so and these numbers about numbers of deaths are extremely they are debated, right? So the case of Chernobyl, right? In the case of Chernobyl, for a long time, the official Soviet figure was 31 people died from that accident. Okay. And in the case of Fukushima today, you will hear people saying there are 0 deaths from Fukushima. Right? That is sort of simply implausible from a scientific point of view, because we can actually estimate what kind of radiation doses are. We know a lot about radiation and health, and how many cancers are caused per unit of exposure, et cetera, et cetera. Again, you can run through the numbers and you will find much larger numbers, right? In the case of Chernobyl, the data from the UNSCEAR, the United Nations Scientific Commission on the Effects of Atomic Radiation, they estimate something like 600,000 per-sievert as they estimate. This was way back in 1993. It probably must have gone up, but they have not produced newer numbers. But even at that number, if you use the standard conversion ratios, for example, from the Biological Effects of Ionizing Radiation Committee from the US National Academy of Sciences, you will find that Chernobyl must have led to something of the order of 35,000 deaths. Right?
Yes.
And if you use those figures and you compare that with the amounts of kilowatt hours that are generated, I'm sure you'll find higher numbers. Right?
No, I mean, the source that it's actually there is site our wrote in data, and it's cited this United Nations Scientific Committee on Effects of Atomic Radiation. So the source says that they take into account this data, several sets of that data. So they actually take into account those numbers that you said. So they say something like 400 deaths from Chernobyl and 2,000 something deaths from Fukushima. So yeah, the question might be more of like you say that some numbers are hidden, maybe some are covered by, but how can you measure how can you find the right information if the let's say agencies that are on the site that are responsible for correctly measuring the casualties might provide incorrect information.
That's a complicated, it's not a question that I can give you a straightforward answer. Obviously, there are people who study these things for years and years to try and uncover these numbers. It's not something you can go on the internet and find a reliable number. I think some of these numbers have to be treated as inherently political and problematic, right? And so you have to look at who's providing it. UNSCEAR has a certain politics, which people have talked about. I mean, I mentioned the example of Kate Brown's book that she talks a lot about some of these agencies. UNSCEAR, by the way, will not give you a number of the number of deaths, okay? They only talk about what is the total radiation exposure, right? And again, the reason they don't give you the number of deaths is because they find that number will be too high. And so they would be very cautious about mentioning that. And again, there's a lot of politics involved here. It's not a low stakes game. It's a very high stakes game. Anyway, okay. We can talk about this offline if you like.
Okay, yeah. Thank you.
Let's proceed to the next question by Dennis on that.
May I ask
about the cost? How does this role of subsidies in renewables? How does it, subsidies in renewables and subsidies in nuclear energy? How they what's the comparison there? And also, maybe I think it would be great for the audience if maybe if you mention about Germany, the case of Germany, their transition away from nuclear benefits and for basically what happened with the environmental impact as well as economic impact. Thank you.
Yeah. So the question of subsidies is a pretty complicated one. It depends very significantly on where it is that we are doing the comparison. Different countries give different kinds of subsidies, and some of these subsidies are pretty non-straightforward to calculate. So I don't want to I think this is not the right occasion to be able to talk about it, but I think the case of Germany is interesting. So Germany, as you might know, decided to phase out nuclear power. But this decision was made way back in around 2000, when a coalition of the Green Party and the Social Democrats came to power. And there was a brief period when the Christian Democrats came to power under Angela Merkel, who reversed the decision in terms of trying to figure out how long the phase out should happen. She didn't change the phase out decision per se, but she allowed nuclear reactor operators to operate for longer than they had been under the phase out law. And after Fukushima, she reversed that decision. And so they had to still phase out by the original date. It was extended slightly because of Russia's attack on Ukraine and their gas supplies and so on and so forth. But the data from Germany has been remarkably interesting. So there were a couple of very brief increases in their consumption of fossil fuels, either coal or gas, immediately after Fukushima in 2012, and then immediately after the Russia's attack on Ukraine. But in both cases, those numbers came down pretty quickly. On the whole, you can say that the increase of electricity supply to Germany's grid from renewables has and their increases in energy efficiency, or the amount of energy they save because of efficiency measures, has more than exceeded the amount of electricity they used to get from their nuclear plants, right? So it's if I remember right, the figure of how much they lost, how much they used to produce from nuclear plants was around 106 terawatt hours. And just to put that in comparison, but the country that is most often contrasted with it was France, and in France's case, its nuclear production has dropped by something like 129 terawatt hours between 2010 and 2022 because of lots of problems with their nuclear plants, right? So anyway, the bottom line is, I think, there are you can always find mistakes in Germany's decisions and different policy channels that they have chosen to implement those decisions. But on the whole, it's a good story that they have managed to successfully move away from nuclear power and also reduce their consumption of fossil fuels while increasing energy efficiency and renewables. And also, just as a side point, their grid is pretty stable. It's not as though their renewables have made their grid unstable. Okay, I see there are lots of other questions, so maybe I should try to keep my answers shorter.
Thank you. We have raised a hand by Mr. Kulmentyev.
Thanks. Professor Ramana, thank you very much for a very interesting presentation. What can you say about such problem as uranium from ocean water as unlimited source of nuclear fuel in the future? The experiment is very popular in Japan, as I know. Thanks.
Mm-hmm. Yeah, there is a lot of uranium around in the world. There is no shortage of uranium. Yes, ocean water can be one source of uranium. There's also uranium from poorer quality resources in terrestrial areas as well, which is typically not being mined because the price of uranium has not risen to the level that is required. And that's actually also the challenge with trying to get uranium from the ocean. You basically have to use some kind of a catalyst to try and capture some of the very low concentration of uranium in the oceans and have a large amount of water that has to go through. So you'll have to go to some area where there is some enormous tidal flow or ocean current and insert some kind of a net that has this catalyst, which is capturing some of the uranium. You take out the thing, you do processing and stuff like that. All of that is a very expensive process. And they are not, I think, economically justified given the fact that uranium prices around the world are not high enough. If you try to do a comparison for how much it will cost, it'll probably cost several times that of uranium from mines and around the world. Japan is particularly interested in it because its government is very interested in maintaining nuclear energy, and it has relatively small land area, so it's always concerned about losing access to fuel. But I don't think it's a justifiable concern. It's definitely should not be of interest to most countries around the world. So as a scientist, one can be interested in it, but I don't think there's any practical policy reason to do it.
Thank you. So we have one question from chat from Sergei Bengus. Does this mean that in total we are increasing the global radioactivity of the Earth? Are we increasing the total mass of radionuclides on the planet due to such nuclear reaction carried out by us? Please.
Yeah, the simple answer is yes. many of these, measuring total radioactivity is kind of a slightly fraught process because each radionuclide is different. They have different impacts on the human body and so on and so forth. So you cannot compare, X number of becquerel of uranium with the same number of becquerel of, let's say, cesium-137. They have very different impacts. But that said, when you operate nuclear plants, when you explode nuclear weapons, you are always going to create nuclides, radioactive substances that are simply not present in the earth, right? Before 1945, there was no plutonium except in one sort of very unusual arrangement in Gabon underground, when there was a brief period when there was some criticality. But by and large, all of these radionuclides are artificially produced, humanly produced, and those numbers are going up as you keep operating reactors.
Okay. Thank you. We have a question from Alexander Borisenko.
Thank you very much, Professor Ramana, for your very stimulating and educative talk. My question is simple. Do you know a realistic alternative to nuclear power stations? I mean, well, for example, such regions like Europe or North America, when from one hand you have a very urbanized, very populated area, industrialized heavily area, and from the other side, not so many windy hours, not so many sunny hours. I mean, can you mention a viable alternative that can produce energy 24/7 and all over the year?
Yeah, great question, something that comes up quite a lot. So the first thing I want to mention is that I don't think we are particularly reliant on nuclear energy, okay? There are specific parts of the world which have relatively high percentages of their grid being supplied by nuclear power plants. That includes Ukraine, I know. That includes France and certain parts of Western Europe. But globally, as I mentioned, nuclear energy produces less than only around 9% of the globe's electricity. And if you think about it in terms of energy, as opposed to just electricity, then it's probably around 4%, okay? So the average person on the earth requires, nuclear energy for maybe 1 hour of each 24 hours, okay? And the kinds of, how easily you can supplant and so on, I think technically speaking, I don't think there's a big challenge. There are specific places where this could be a difficult issue. And you will have to think about, is there alternatives in terms of going to offshore wind? Can you supply electricity from elsewhere and things of that sort? But at a global level, if you think about the total amount of energy we require, and how much energy comes from solar and wind sources, I think there's no comparison. The issue that you mentioned, I think, about how do we do 24/7 and what is the kind of, what usually is called baseload electricity? That, I think, is a more interesting question. And there I would say two things. First is, I think the idea of having 24/7 power is a leftover from an earlier era of energy planning, where the grids were largely dominated by either nuclear plants or coal plants, or in some cases large natural gas plants and so on. These plants, for both technical and economic reasons, prefer to be operated at that 24/7 level. You don't want to shut down a nuclear plant frequently or raise or lower its power levels because there are safety implications for that. And there are also implications for the wear and tear of different kinds of equipment, right? And so old grids were sort of structured around these sources of power. But we must remember one thing: the reliability of a grid, the fact that it can supply power to you upon demand, is not a function of individual generators. It's a system level property. It's an emergent property, right? It depends on what each of the components of the grid is doing at any given point, right? And so the idea of the grid's reliability being based on any individual source of power is a wrong one. And I don't think any grid manager will think that way, because each of the nuclear plants and so on will also have to be shut down during certain periods of the year to refuel, for maintenance, things of that sort, right? So nothing is going to be constant all the time. Now, because of climate change reasons and because the cost of renewables have come down such a lot, the proportion of our energy that comes from these renewables has been going up. Now, renewables don't fit either the picture of being base load or what used to be called peaking plants, which are intended to supply variations in power and demand. And so what you now have to do is to actually structure your grid around these renewables. When you have a lot of renewables, there are going to be times of the day, of the year, when they will meet all of the demand. And because renewables have fairly low, in fact, almost zero marginal costs, you would probably want to use them as much as possible. Okay, what does that mean? That means that there are going to be times when renewables will meet all of the demand, which means all of the other plants will have to be shut down. So no plant will be operating 24/7 in a grid where renewables even form a substantial fraction. Let's say a third of the electricity comes from renewables, you will have to shut down all the plants at some time. How do you deal with the variability of renewables? I think there are three broad buckets that you can think about. The first and the most obvious one, but in a way the most expensive way to do it, is to add storage through using batteries and various other storage technologies. But that's the kind of obvious one. I think there are two other important things that you can add. One is a traditional one has been the use of diversity in technology. So you're not using just solar or just wind, but use some combination of certain kinds of solar plants, thermal plants, photovoltaics, offshore wind, onshore wind, etc., etc. And using this combination, you're going to be able to have much greater reliability than just with one technology. Also, geographical diversity matters. So if the wind is not blowing in Spain, maybe it is blowing in northern Germany. And if the grids are connected, then that can be another way by which you can manage for that. And last but not least, there's also variations in the demand that you can be managing as a way to manage the variation of this. I think I'm out of time, so I'm going to stop. Otherwise, I can give you a longer lecture on that particular aspect.
Okay, this means that your advice is to build a grid, to advance storage, and to optimize consumption. Yes?
Yeah, to be able to do demand side management. So variations in, to give a practical example, when I used to live in India, we used to have a lot of blackouts, right? And what the grid managers would do is to tell us when they are going to shut down the grid. And during those hours, we will try to not plan doing anything, but we'll do our work, whether it is cooking or whether it is using the washing machine. You do it before the period when the electricity is going to be shut down, right? Now, this can be automated in many ways in today's grids.
Thank you. Thank you very much.
We have a question from Sergey for me.
Hello, thank you for your presentation. It's not a question, it's maybe a remark. I don't agree with the majority of arguments what was done for the nuclear power, this presentation, but it's needed several hours to answer and to make a discussion. So maybe I will propose another seminar on this item, and with my vision about this problem. Yes, and what is my remark? That all the people in social society and historical scientists very often speak about the dangers of nuclear power technology. But in our world, we have a lot of dangerous technology. I can speak about the genetic engineering and so on and so on. And the most important dangerous for our humanity, it's the political regimes in many countries. Of course, with nuclear weapons, of course, it's a huge problem, I agree. And I'm against this problem. But such a presentation never make a comparison with, for example, road traffic accident. Each year on the Earth we lose 1.5 million people died on the roads. They never speak about the smoking. The smoking gave 8 million per year now deaths directly connected with smoking. But why you don't speak against the smoking people? And each day, each year, the number of smoking people increase 20% per year. So when we speak about the dangers of nuclear power, you have to compare. Even if you compare with hydro power production energy, you will see that it's 1,000 times more dangerous in calculation of deaths. You know the accident maybe 1975 in China, when it was tens million people deaths after they broken the dump on the rivers at several dumps. Was also in Italy. So you have to compare and to be honest. Okay, thank you. Nevertheless, your arguments reasonable, but I have anti-arguments for next time. Okay, thank you.
Thank you. I mean, you know, whether they want to organize another seminar, that's of course up to the organizers, nothing to say with me. I'll just only one thing. I think the idea that you have to compare different kinds of risks is valid only if you are thinking about it in comparable areas. So I don't see what's the point of comparing this with number of smoking. I'm not endorsing smoking, right? And likewise, with you know, the usual point which they'll say is number of deaths from fossil fuels, but I'm not endorsing fossil fuels here. So I don't think these comparisons are important. Last but not least, I think there are also very different kinds of risks in certain cases. So in the case of smoking, for example, a lot of the time, the risk is something which you're either undertaking knowing it or because it gives you a certain kind of pleasure, or it is happening because in certain areas it is not restricted, right? There is secondhand smoke and so on and so forth. So when there are risks where you have some control over, for example, when you drive, there is a risk. We all understand that. When I drive, I know there's a risk, but I also know there's a benefit, right? The question is whether nuclear energy gives you the kind of concomitant benefits, and the answer is no, because nuclear energy is very expensive, right? So I think that's the other part of the thing. The issue is not that only risks. It's also when you have to compare with the benefits. And in my opinion, the benefits are much less than the risks and the costs of nuclear energy. You may have a different opinion, but that's fine. That's your opinion.
In the long term, development of
I should actually go because I have another meeting. So I'm going to actually sort of stop here simply because I have to go to another building and I have a talk in about 15 minutes. So
okay. Thank you very much. Goodbye.
Thank you for all the answers. Perhaps we could stop the live streaming at this moment and let us thank the speaker again and for wonderful talk and for questions and answers session. Thank you very much for all participants as well.
Thank you very much. Bye-bye.
Thanks. Bye-bye.
Thank you.
Bye-bye.
Thank you. Bye.